Hi everyone, today we're going to be starting Unit 7, Equilibrium. We'll start this unit by just talking about a brief introduction on equilibrium and what this actually means, and what it means for reactions that are under equilibrium. So I'm going to start this by thinking about a reaction that we've seen on 2 exams now at this point, and we've looked at different kinds of situations of this reaction, and that is N2O4 decomposing to form 2NO2. We always write reactions with one arrow going forward. So if we have one arrow going forward, that basically means that it goes to completion. In other words, all moles of N2O4 react to make 2 moles of NO2. So if I have 1 mole of N2O4, I make 2 moles of NO2. That's what completion means. In reality, this reaction is under what we call equilibrium. And you draw these 2 sets of arrows. And so equilibrium just means the rate of the forward reaction is equal to the rate of the reverse reaction. And we won't discuss now, we'll talk more in Unit 5 about what I mean by rate and how we can actually calculate things from this. But what I'm essentially saying is that for the forward reaction, which is N2O4 goes to 2NO2, this reaction is happening at the same rate as the reverse. The reverse reaction, of course, is just the arrow pointing backwards, which is 2NO2 reacts to make N2O4. And so what these equilibrium arrows here say is that I have a forward reaction, but at the same time, I have that reaction running in reverse. And we can actually depict this in terms of a graph. And so let's say here, I have concentration in molarity. And on my x-axis, I have time. We'll call this seconds. It doesn't really matter what the unit is, but we'll call it seconds. Now, over the course of the reaction, your concentration of NO2 is going to increase until eventually it reaches this plateau. It'll be flat. So this is a concentration of NO2. If that's increasing like that, what's going to happen to the concentration of N2O4 is that this is going to decrease until it also reaches a point where now the concentration is constant. And this is the concentration of N2O4. And so once these both are constant, this point meaning constant concentration, constant concentration means that your reaction is at equilibrium. Or in other words, you're going to make a bunch of NO2 until the change in concentration is constant. You're also going to keep reacting N2O4 until the change in that concentration is also constant. Now what this means is the amounts of product and reactant are constant, not necessarily equal. What's really important to remember is that what this does not mean is that the reaction has stopped. That's not what this means. The reactions haven't stopped. It's just that the forward reaction happens at the exact same time as the reverse, and they happen at the same rate, meaning one is not faster than the other. And so I'm going to put here with a big star, reactions have not stopped. When something is under equilibrium, that reaction has not stopped, either the forward or the reverse. All it means is they're happening at the same time and at the same speed. Now here's a few examples of different types of reversible reactions that we encounter. One is the evaporation and condensation of water, right? Once you start boiling water, some of it is still going to condense back into a liquid, while some of it is going to boil and turn to a gas, right? And so it's under equilibrium. You'll have some boiling while you'll have some also condensing. Adsorption or desorption of a gas by a solid. So for example, in this case, we'll take C2H4, which is ethene, react it with hydrogen, and this is in the presence of some platinum, and you'll make C2H6, which is ethane, right? This reaction will go forward, but at some point, the rate of that reverse reaction will equal the rate of the forward reaction, and so you'll go back to ethene and release some hydrogen. Dissolution slash precipitation of a solid, normally we think of this as going all the way to the right, but for some solids, you can actually have it also go right back into the water because they're not super easy to precipitate, right? They want to, but they kind of like water just a little bit. Proton transfer and acid-base reaction, this is extremely common, and we'll really see this a lot in Unit 8, right? If I have some sort of a weak acid and a weak base, we'll make a conjugate base and conjugate acid here, and that can also go in the reverse reaction, right? It doesn't necessarily have to go to completion, especially if you have weak acids and bases. And then transfer an electron in a redox reaction. So in this case, H2 plus I2 will make 2HI. You can actually go in the reverse direction as well and make H2 and I2 again. And then again with these two metals, right, we think of this as transferring electrons, but technically the reaction can go right in the reverse direction and transfer electrons from the copper over to the iron. There are many, many examples of reversible reactions, and as we move on through this unit, I encourage you to always think of the fact that a reaction can technically go in reverse. We'll talk a lot more about how we know if a reaction can or cannot go in reverse throughout the course of this unit. For now, that's all. Thanks, guys.